Hi, I'm Kevin. I'm here with Hambo today in order to interview our special guest, Nikita Dhawan, who's a current PhD student at the University of Toronto, specializing in building AI pipelines. She's extremely passionate about using AI in healthcare to improve efficiency as well as accuracy. So let's give it up for our guest today. And let's begin just by looking at some of her work. So I know recently, Nikita, you've published FedFish and worked on the paper in TMLR. Congrats, by the way. For folks who have not read the paper, however, how would you summarize what you've done?
Sure. Yeah, so FedFish was my work during an internship with the Federated learning team at Google. It is essentially an alternate method to implement a federated learning system. So generally in a federated learning system, for anyone who's not familiar, you have a number of clients with some amount of data that they have that is private. You have to make sure that that data is never leaked or never shared across clients. They are able to train their local models on that data. So the premise is that we want to train some model on data. The data is decentralized among different clients. And then we want some way to aggregate that data at a central, what's called a server, or train a global model. And typically, the sort of canonical method for doing this is that clients can, or local models can be trained separately. They can be, the model weights or parameters can be sent to the central server. And then those are aggregated, typically just averaged, like a parameter average across all clients. What we did with FedFish was to take output space instead of a parameter space, an output space view of this kind of aggregation. And we said that what we really care about is not aggregating parameters. What we really care about is trying to build some aggregate function that represents the functions, the mappings from inputs to outputs for every client. So if we are allowed to send a little extra information along with just the parameters, we can actually approximately try and fit the actual functions from inputs to outputs that those parameters represent. And we sort of showed that like when you do longer training on client sides on local models, this can be much better than something like just averaging, which has sort of well-known pitfalls when you have longer training. So that was the idea. Yeah, I'm happy to go into more in detail if you have specific questions.
Yeah, I think one thing that would help everyone maybe understand a little bit more about federated learning is listing like a few use cases. So, for example, in what instance might there be a bunch of different users with their own personal models that a
Yeah.
more global model needs to be built upon?
Yeah, so I think a very intuitive use case would be anything to do with healthcare. So healthcare information is often private for good reason. We don't want to share that. Hospitals will often not share that across across each other, like across different hospitals, or even with like global agencies, they might not be willing to do that. So instances where you might want to train a model within, say, a hospital on that hospital's data, but then eventually you want a global model where you have good capabilities across all populations in all hospitals in some region. So that would be one use case, to try and have different hospitals train their own models, collect those models, not collecting the data itself, because that's private, and then aggregate that. I think there's several other use cases, for instance, functionality that is sort of on device. So if like mobile phones and such are being used to collect data of some kind, and then train some models to then produce recommendations, of course, users don't want that data to be shared globally. So if the models are small enough, can be trained on device, then those parameters can be shared globally without actually sharing the data. So it's another use case, which I think actually is practically something companies like Google do think about and do implement in their products.
So, in comparison to, let's say, sending data from personalized devices to, let's say, a global model to be trained upon, is there like performance differences you've seen with federated learning? Yes, maybe being less secure with personable, like identifiable information in that sort of parallel?
Is your question, is there a difference in performance with and without maintaining the privacy?
Yeah.
Yeah, so there definitely is. I think you can think of the oracle of this system to be, you have no constraints on privacy, you have access to all your data, and sort of the best thing to do loosely speaking, would be just collect all that data and train on that data itself a global model. That would be like the best case performance. And that's sort of an upper bound on the performance. Even when developing research methods, we tend to sort of report that performance or talk about that performance as like the absolute upper bound. And the closer you get to that, the better your method is. So there's definitely a performance gap and a performance drop when you're not allowed to see that data. And you're only allowed to see parameters because there's, in some sense, a loss of information because you're losing some of that information, whatever's stored in the parameters, that might not recover the functional relationship between your data and its out, and the input data and its output. So there is a performance gap. That's sort of like the key challenge of federated learning, to reduce that performance gap as much as possible under the constraints of data sharing.
Could you share some of the results when comparing to like that Oracle benchmark between how federated learning works versus how like open access to all data might look like?
Yeah, sure. So we looked at that in a sort of toy setting. So in our experiments, we sort of looked at synthetic toy settings to really understand what is going on under the hood, and then also way scaled up settings where you have a lot of data and you really want to like test performance on something that's more realistic, that's not toy. So in the toy cases, we were able to, look carefully at what the Oracle would do and how we compare to that. So if we construct a toy case to really demonstrate the setting that we looked at, which was that our approximation of the function represented by the parameters is good enough, then there's a figure in the paper for anyone who's looking into that, where we show that really if you have two different clients, for instance, that have some data that is, might be on disjoint supports, which means it might just be like disjoint, not overlapping input spaces, then something like parameter averaging would just sort of find like the average between those functions and represent neither of them well. What the Oracle would do would have all of that data together, so should be able to represent the functions for the entire data set if you've trained a model good enough just using standard machine learning. And then what we showed was that with our method, we get way closer to what that Oracle would do, that we can actually, because it's a 2D toy setting, you can actually get way closer to the real functional relationships between inputs and outputs, and be way closer to the Oracle than something like just direct parameter averaging. It is also something to look at. So this is a toy setting. In the more realistic settings where we looked at like actual data, language data, also image data, we get closer to the Oracle again, but not as close. So the gap, so there is still a lot of work to be done and a lot of like potential for improvement in future work to sort of measure this functional relationship better and approximate it better. So in those cases, we get closer than parameter averaging does, but we're not quite as close still. So we're not there yet. And better approximation, we believe better approximations to the functions represented by the parameters should get us even closer, because that's really, really what we're trying to measure. Yeah.
Yeah, so for anyone following along with the paper, she's talking about figure 2, in which you can see the FedFish global function is a lot better than the Fed average global function when it comes to trying to match the distribution of two different data sets. And so, yeah, this is really interesting work. And I think one thing we should talk a little bit more about is future directions, because I know a lot of people in our audience might be really interested, because federated learning has like a lot of potential when it comes to privacy as well as when it comes to actual healthcare applications. So what is like some of the most promising directions that people can take when it comes to maybe improving the accuracy of like federated learning in general?
Yeah. So in the same vein as this work, I can say, so here the thing that we tried to approximate was this functional relationship, right? So really, instead of trying to match the parameter spaces of two networks, we're trying to match them in their output spaces given some data. What would be really, and the way that we did this, we made a very simple approximation. Actually, we just did essentially a linearization approximation. We've said, let's pretend that our network is linear in its parameters, and then you can sort of use the first order Taylor expansion, which is essentially linearizing the network, and say what information you need in order to predict the outputs. And it turns out that you just need some gradient information. You don't actually need any data. But now this, you can imagine, is a very, very crude approximation. We're assuming that a neural network is linear and then trying to match the function outputs. That is not true. No one really trains linear neural networks anymore for anything that you want, high capability on. So a direct question to think about as a follow-up or future work is to think about what would be better approximations. So can we do either higher order approximations while still not having to? So the challenge is, if you have higher order approximations and more fine-grained approximations, you're likely going to have to send more data from the client side to the global server. And so there's a trade-off there. So to think about which trade-off is okay enough that you can make a better approximation, a higher order approximation, and get better performance while still maintaining data privacy. If there is more data that needs to be communicated to the global server, are there sort of privacy techniques? So there's this whole field of sort of masking data, or even like using differential privacy, using these privacy techniques to actually mask things that can then be recovered at the global server in the sense that they need to be. So yes, I think those would be a couple of things. Either try to improve the approximation to get higher performance, and or improve like privacy techniques so that you can actually send across more information, get better performance while still maintaining that privacy constraint that federated learning has.
I want to double click a little bit more on like the stuff that your paper actually did when it comes to linearization and how that was able to work within federated learning. So our audience might not know as much as you do, obviously, about machine learning and how these concepts really work. So could you give maybe more like bird's eye view vision of what the paper did here?
Sure, yeah. So in terms of the methodology, we made a simple approximation that in other works has been sort of well explored. And that's what I'm calling linearization. Really what that is you pretend that the one neural network, maybe on one client side, is a linear function of your global network. And what that looks like is basically writing down the Taylor expansion. I don't know how familiar people are with this. I'm trying to think of like a better concept that might be more familiar, but essentially writing down an approximation to that network such that it is always going to be a linear function of the global network. And what that function depends on ends up being the global network, the actual network, and some gradient, some derivatives, first order derivatives. And generally, if you take higher order approximations, you would need higher order derivatives. Eventually, when we make these approximations and one or two other assumptions, such as that the network has actually converged, the network is, that has been trained is actually optimal for the data that it's trained on. What we end up with is some aggregation formula, which just depends on what's called the Fisher information. The Fisher information is second order information, so it's kind of like second order derivatives of your function. We further have to approximate that because the Fisher information is this giant matrix which has the size number of parameters by number of parameters. Generally, parameters go in thousands nowadays, millions and billions of parameters. So we want to approximate that somehow. So we make further approximations. We say, okay, maybe it's a diagonal matrix. Let's just assume that we only need the diagonal. Now we've already reduced the number of the storage of that entire matrix by a huge amount. And then let's assume that we can approximate that using the gradients of the network itself. So if you have the gradients, a very crude approximation to the diagonal elements of this matrix are going to be just a squared gradients averaged over your data. So that's essentially what we end up doing, computing all those things, communicating the gradients and the squared gradients to the global network, and then aggregating using a formula that I won't spell out, mostly because I might just misremember it. And also, I think it's easier to look at if you're looking at the paper, but there's this formula that will just aggregate all of this, all the models using their gradient and squared gradient information, and give you the approximate model that matches each one in function space. So this would be an exact method if they were actually linear functions and if we had the actual Fisher information matrix. But then given these approximations, which are really the reason why performance drops, we're able to do this for settings, even when that's not true. And we sort of empirically test that it still does better than what we have in terms of average parameters.
See that there is a term called client server barrier as like the benchmark into evaluating Fed average and FedFish outputs. Could you like go more in depth about how exactly like this benchmark like evaluates these two?
So really the idea there was when we were looking at these different federated learning methods, and what we were focusing on in that entire system of federated learning was the aggregation technique. We weren't really changing anything about how training is done locally, globally. It was just, just locally. Globally, we were changing how the aggregation is done. And one thing we realized was that it didn't make as much sense to us to measure performance just in an absolute term, just measure like the global model's performance with FedFish versus Fed average versus something else. We realized if we're looking at aggregation, what we really should be doing is comparing how well the global model is actually matching the local models, or the servers matching the clients. So that's really what the client server barrier is. It was this evaluation criteria that we came up with, given any loss or accuracy or any other evaluation criterion that you're interested in. What we wanted to measure was, what is that loss for your clients? What is that loss for your global model, and what's the gap between those? And hence that's called the server client or client server barrier. So we felt that that would be a better way of measuring how good an aggregation technique is, because as you change at every time step, as you change the aggregation technique, one thing that I should have mentioned earlier was that in federated learning, if you have multiple rounds of aggregation, so the clients have trained their models, send them to the server's aggregated them, the server sends out that global model again to the clients, does another round of training at the client level, again, they send it back and then repeat. So now if I've changed my aggregation technique, that means the model that I've sent in round 2, for instance, to all the clients, is now different than I would have had with a different aggregation technique. That means that model, which serves as the initialization for those clients in round 2, is now going to be a different one. And so the local training is just going to be different. So it's not really comparable to measure the final performance of a model when you've had different aggregation techniques. And so now the local training has been different in every round. And so to sort of remove that kind of confounding factor, we looked at this average barrier, assuming that the clients did the best training that they could locally. What is the barrier between their model and the aggregated model at the global server side? Just to understand better what difference our aggregation technique was making. We sort of didn't want to catch any differences in performance that were due to anything except for the aggregation technique. That might have been due to a slightly different initialization in a different round, or something else that got changed because of a different aggregation technique. So we really wanted to just measure how the functions have changed when you aggregate. So that was the idea behind measuring that, and then we sort of had those results to show that that barrier in a lot of cases is lower when you take into account functional relationships, which FedFish is an approximation of, which is just further motivation that that's really something that we should try and approximate and try and communicate between servers and clients. Does that answer your question?
Yeah, thank you.
This is really impressive work. But I think we're going to wrap up on our discussion of federated learning like right now, and then move on to your second paper that you're really enthusiastic of discussing, which is natural. Nikita actually published this paper recently on behalf of the University of Toronto at NeuroIPS, and it's basically, putting in her own words, end-to-end causal effect estimation from unstructured natural language data. So Nikita, do you want to maybe do another summary about the work you've done, the impact your work has had? Yeah.
So this is almost my most recent work, very close to the most recent thing that I've been doing, and it's really something that I'm actively thinking about even now. So like you've said, I'm very excited about it. The idea here was very motivated from healthcare settings. So I'll maybe give a quick motivation from that respect. Really, this is applicable to anything in which we care about causal effects, which is really almost everything in the world. So as a quick aside, things like business decisions, marketing decisions, all of those things fall under the framework of what we did here. But you'll see if you look at the paper, if we talk about the results, that this was very much motivated by healthcare questions, which is what is the causal effect of some treatment on some outcome for a population of individuals who are suffering some disease. That's sort of the setup. And more specifically, you can think about cases of drug repurposing. So what we, and why I specifically say that will become a little bit more clearer once I maybe lay out like where our data comes from. But drug repurposing is basically this idea that, there are a lot of drugs that have been approved by the FDA for certain diseases. Doctors are not allowed to prescribe them for a different disease unless there is evidence that that drug can be repurposed for that other disease. So it can actually have a beneficial outcome for individuals with a different condition. And in order to do that, what would have to happen is that that drug that has gone through clinical trials and has been approved by the FDA would have to again go through a clinical trial, this time for a different population for that other disease, measuring different outcomes that it could be repurposed for, and then it can be prescribed. Now, we started out working on this, believing that there is a lot of potential for drug repurposing. So there's some classical examples since the longest time. And I think one of the oldest ones is aspirin, which wasn't always a painkiller. I believe it was, I think it used to be a painkiller and then started being used for blood thinning as well. And now it's commonplace for that use case. But if you look at the history of it, it actually took decades and decades for that to actually get approved as a blood thinner. So that's a long time. And that is leaving things up to chance a little bit because the doctor happened to realize that, oh, this is actually helping some of my patients who would benefit from blood thinning functions, and then happened to realize that that might be something useful that should be researched. So that's sort of leaving things up to chance. And what we wanted to do was make that systematic. We wanted to see how can we actually go out, look at, gather patients' experiences with some drugs, see if they've noticed things, because really like patients are the ground zero of like that information, and then see if there's potential for repurposing drugs. And what then needs to happen is we need to measure causal effect of that drug on some other outcome and some other condition other than the one that it has been approved for already. So that's like the large motivation. The other bit about that motivation is just that these things are really expensive. So if we do want to look for these, potential repurposable drugs, we don't really want to send just about every guest that we have to a clinical trial, because that's going to take years and it's going to take millions of dollars. And that's going to, most importantly, be a bit of a risk to humans because humans are being tested. The drug's being tested on humans. So we want to have some more information than just random guessing. And the insight that sort of led to Natural was that there is a lot of this information on social media, on online platforms, on forums where patients actively go and write their experiences. One of those places actually is Reddit. So Reddit has multiple subreddits dedicated to different diseases, where people will sort of go and, amazingly build community and also make that a very information dense and very rich source of just patients' experiences with different drugs, the side effects that they've noticed, the other good or bad, effects that they've noticed that they didn't expect to, or that the drug wasn't supposed to do. And we sort of wanted a way to aggregate all of that information. So that's why in the title it says unstructured natural language data. So we realized that there's all this data that's completely unstructured. It's all in language. There may be other modalities, but a huge amount of it is in language. And we need a way to extract some causal insights from it that's not a human just going through it and reading it and trying to make notes about that. And the reason that this became more recently possible to do is because of like the huge amount of capabilities that large language models are giving us. And we tried to basically figure out a way to structure this unstructured data to come up with what quantities do we need mathematically in order to actually measure a causal effect. see if we can use an LLM to approximate those quantities, again, under certain assumptions that we have to make, and then measure the causal effects of these different settings. So of different treatments compared to either other treatments or no treatment. We generally compare two treatments against one another, and what effect they have on some disease. And this was really mind-blowing to us because typically someone would have to go through this kind of data, write down, make a table of all the observations, and then pass it through a causal effect estimator. And that's a lot of time, a lot of effort, and would be prone to a lot of error even. So we were really excited about the possibility of sort of doing this in like a day using maybe $100 or $200 of compute in terms of LLM credits, and actually come up with repurposable options that could be repurposed as drugs, and essentially definitely not recommending those repurposed drugs, but prioritizing them so that they can be sent to a clinical trial, and that process can be sped up so that more diseases which don't have any approved drugs can have them. That's the large motivation of this work.
So on the note of like natural, I know that it takes information from online health forums like subreddits and stuff, but then I've also heard that there are a lot of misinformation on these same forums. So how would natural be able to sift through all of this misinformation to get down to the core of the problem?
Yeah, that's a really good point. And that's definitely a big concern, especially when you look at these. Reddit is moderated to some extent, but definitely like the truthfulness or like, as you said, like checking for misinformation is not like foolproof. So what we did, we came up with, so we looked at a lot of other work that, scrapes these kinds of websites or this kind of data to find data for their use cases. And we came up with a multi-stage filtering pipeline that, to the best of our ability, again, not foolproof, but to the best of our ability and our knowledge, can filter out the things that we can think of would be not likely to be true, not likely to be relevant, could be a bot, like we actually did, like filter out things that are likely to be just like a bot saying stuff through certain rules. And some of those rules we came up with, some of those rules we looked at like other literature. So there's a good amount of literature looking at how to actually collect data and filter data and use it, this unstructured data. It hasn't used it for causal effect estimation, but a lot of those techniques and insights are directly transferable to this kind of use case. So we sort of relied on these, NLP, these natural language processing works that already deal with this problem and get that in. At the end of the day, this concern is still really relevant and a big problem even now, even in the current state of natural. I wouldn't say that it's completely solved, because there can be things, and I think it deserves a lot of attention. Sort of like look at your final set of filter data and make sure that that's vetted. One thing that I'm excited about is to actually move to data sources that are more vetted, if for lack of a better word. So things like publications, things like clinical notes. So more like medically approved forms of data points, which are also language most often, and are very often not structured. But those are definitely, coming from a medical either institution or written by a approved licensed medical practitioner, and it's just a more trustworthy source of data. So I think that would be one other way to go to sort of like mitigate that problem. But in general, it is a concern, and it is something to be careful about and to sort of put your final filter reports through checks, whether it's like randomly sampling data and looking at it, or having experts look at it, or just developing like a really robust pipeline that throws out garbage, which is what we try to do.
Do you think that in the future it'll be possible to like, because I know that in your when we're talking about federated learning, you said that with more like data, you'll be able to like train the model better. But for natural, do you think it will be better if in the future you could get your hands on like autopsy reports or like maybe opened medical files of like patients who have been recently deceased or things like that? Do you think that will significantly contribute to the accuracy for natural?
Yeah, the kind of data and whether they are autopsy reports or not, that sort of does depend a lot on the exact experiment or the exact problem setting. So if it is a problem setting that is, for instance, looking at the effect of some drug on mortality, then definitely something like that would be very relevant. And if we could get our hands on that data, that would be that would just be, the more data we have, the more sort of representative it would be of the population that we care about, the better we can construct an estimator for the causal effect that we're interested in. Because you mentioned federated learning, I do think that it would be the one line of work that is extremely important and interesting is how do you actually combine. So again, as federated learning aggregates different models into one global model, here we're not really training new models. We're using models to sort of estimate a causal effect. But how would you aggregate different causal effects from different data points? So I can imagine a setting where sort of hospitals maybe don't want to share this data, or they don't want that data to, be fed into some LLM that is, not housed privately or that they don't have access to. Or they do have access to, but they're not the ones sort of feeding it in and making sure that the data has been like vetted for that. So they might want to run this kind of thing locally, compute the estimate that we ask them to compute, given our sort of pipeline and the code base and everything, share that estimate, and we figure out a way without having access to their data, without having access to like really any of the structured information that we need to compute that estimate, figure out a way to aggregate that causal effect with a different hospital's causal effect and combine those in a meaningful way. So that is a bit of an open problem. There has been some work in the causal inference literature of how to combine different effect estimates in a way that still makes it an unbiased estimator or a consistent estimator of your problem. But those still depend on a lot of assumptions. Usually they'll, again, assume something like the models are linear or something like that, which is not the case. So coming up with better and better estimators, better and better aggregation techniques like that, which is sort of in this federated learning spirit, again, it would be really useful to, make this practical. Because right now we did what we can do in an academic setting, but to really make it practical and make it usable in the real world, there are going to be these kinds of constraints of like privacy, access, and such. So yeah, again, really good point.
Thank you, Nikita. And so now that we're on the topic of medication, and like the medical industry, I just wanted to know which like incident or like what interactions you had with the medical industry that inspired you to connect it with machine learning and artificial intelligence.
Yeah. So I've been lucky. There have been a lot of people at University of Toronto. So like you guys introduced me with, I am a PhD student at University of Toronto. There's a good number of people who are doing a lot of interdisciplinary work here. And a subset of those people are people who are thinking about ML for healthcare or just the intersection of AI and healthcare in different ways. So a part of it is that it just access to these people really gave me exposure to things that are possible. My interest into going into this was very personal. So it's really a combination of both those things. So I only knew that I could do this because I could see other people sort of thinking about it. And one of the co-authors on this paper, Rahul Krishnan, is a professor here who's been doing a lot of work for a long time in causal inference, in ML for healthcare, and sort of like every intersection and every permutation of those different subfields. So to learn about what kinds of stuff he and his students are doing was just made it possible. Other than it being possible to do this work, I had to be interested in it. So I became very interested when I learned about sort of, really the real stories of a lot of people struggling with these kinds of things, with the lack of treatments, approved treatments for so many diseases. So there's a handful of treatments that have been approved, but there's just thousands and thousands of diseases that exist and that people are suffering from. And even if treatments are approved, they're sort of effective for certain populations, not for other populations. So just like the whole the expanse of how big this problem is and how much impact there could be if it was solved made it really interesting to me. A lot of that realization came from the pandemic. from people's experiences with that, from my own experience with the fact that, a pandemic leaves you with very little time to do anything. And we do really want methods that can approximately do things, but like do them fast so that the powers that be can know how to prioritize different treatments. So the effects of the pandemic were obviously devastating for my own family. I lost my father during that time. So that gave me a lot of motivation and a lot of time to think about these problems and think about really what I care about working on. I saw it, cause a lot of problems for a lot of people in my friend circle. Over here with my advisor, he's been very vocal about his experiences, Chris, his experiences with suffering from long COVID effects. Again, something that doesn't have an approved treatment as yet and is not maybe getting the deserved attention that it should. So just multiple cases. Of course, my father's sort of, I think, the biggest motivation for me to think about these things even and to care about them. But even after that, just like multiple cases and multiple scenarios of just people around me who are genuinely, wish that there existed a treatment for something that they're going through, and the fact that that doesn't exist. The last thing I'll say that really inspired this was this startup that they pivoted a little bit, but they used to work on something like this, which was like social media insights. They weren't looking for causal effects. They're called Eureka Health. For anyone who wants to look it up, we did make sure to acknowledge them in the paper, so you'll be able to find their name and the associated members of the startup over there. But they really sparked this idea of that, social media has a lot of this data, and it sort of goes to waste. Aside from the fact that you can go and read it, and people can sort of like really go through all of the comments on Reddit or some other platform to see if something aligns with them. Other than that, it sort of goes to waste because no one's really aggregating that information or structuring it in any real fashion. So from them, we sort of had this idea of what if we look into this source of data? So I think all those pieces had to sort of come together. We had to realize social media is really rich in that data. We had to realize that, learn about causal estimation. I do not come from a causal inference background. This was my intro into that, so learn about that, which my collaborators helped me do, and just generally learn about the impacts of these kinds of things on public health and healthcare. So all of those combined led to this.
Wow. Well, those are I think those are very good. Those are very good inspirations for you to create such a brilliant idea that I don't think anyone before you has ever created. I'm sure that moving forward, lots of people are going to use natural. And after I think we're probably going to wrap up around there. And I just wanted to ask you about something more lighthearted. So what do you feel how do you feel about your entire process of getting a PhD, in your college dive at University of Toronto?
Yeah. Yes, how do I feel about the process of doing a PhD, right? Was the question? Yeah, a PhD makes you feel a lot of things. It's definitely a very intense sort of thing to do. So there's a lot of reasons to do it. I think people have sort of different ones. Being the absolute expert at something in your field, being just having that sense of qualification that you're going to be the only person who can work on that one particular very niche thing. Just the love of research, just wanting to go through a lot of things and understand what has been done and then push it a little bit further. Just that fact of pushing the boundary and being at the very cutting edge is really exciting. And all those things I also relate to. For me, I think the reason I got into research during undergrad while I was at Berkeley, and I really found interestingly enough, found it really fun to do because of the people that I was doing it with. And that, I think sort of the community of people who are really interested in a problem that hasn't been solved before. There isn't a lot of reason to think that it will be solved in the next 6 months that you work on it or the year that you work on it. But you sort of just have this belief that, oh no, I have an insight about this and I have a sort of perspective on this that I don't believe anyone else has had. And I'm going to work really hard, really, really hard and fail many, many times and then still keep trying to solve this. So I think that sort of spirit was really appealing to me. And yeah, I really enjoyed being around those kinds of people, and I figured that I would just try to be one of them myself and continue to stay in that side of work. Other than that, like I think generally a lot of people doing a PhD. So yeah, so that's sort of like how I got into it, why I'm doing this. How I feel about it in general will be very similar to what I think anyone will tell you about a PhD. It's a lot of struggling, it's a lot of failing before you succeed. So we sort of like fail consistently until you finish, until you sort of finish failing or like happen to succeed or whatever. Write up that paper, publish it, and then you sort of like go on to your next round of failing consistently. And I say it in that sense because that's what it ends up feeling like a lot of times. Really what's happening is not that you're failing, you're just trying really hard at a problem that's really, really difficult and no one solves, so no one can give you the answers to it. But it can end up feeling like you're just failing a lot. So I think one common theme is just like building a resilience to that and building this resilience to like many, many challenges, which are not just technical. The bulk of them is technical. Of course, if the problem is difficult, it doesn't work, the experiments don't work, your results aren't as good as you'd hope they would be. You're not quite sure why. But also other than that, just challenges of like bureaucracy or infrastructure or having the resources or the compute or the social aspects of research is actually very, at least in AI and a lot of the computer science things, a very, very social endeavor. So challenges that come with that. So just navigating all of those things very end to end is it's quite something. I don't know how to describe what it is, but it's quite something. It's quite a unique experience, I think, as opposed to being part of a system where you deal with one part, you're dealing with like maybe the very end of like the product building pipeline or whatever it is, or the very beginning, or you're doing the research at the very beginning. So the fact that during a PhD you sort of build everything from the very first like ideation of an idea to like finally presenting it or starting to talk about it or giving a presentation on what you did. So that entire journey of like owning every single part of that is, I think, very unique, which you don't really get to do anywhere else. It's also exhausting because that means you spend like over a year on something, so you'd better be excited about it. But yeah, I think it's really unique. There's a lot of ups and downs. There's a lot of pros and cons, as with anything else. But I think if you're excited about things that are challenging, that haven't been done before, at gaining really deep insight and expertise into some problem, it can be a really good way to have the freedom to do that. Because yeah, academic freedom is also really valuable. That's the other thing. That the freedom to just explore things that might not work out. There are more projects that get tabled, that get canceled, than ones that don't. So there's a lot of projects that you don't see anywhere because someone tried really hard and it just happened not to work or didn't work at that time. And you sort of have to accept that that's always a reality going into something, into some direction. And yeah, to still want to just like continue to think about that and work on that and try to see like what can you glean from whatever you thought of.
All right. Thank you for your time, Nikita. We admire your hard work and we hope your PhD continues to go well, which I'm sure it's doing really, really well right now, considering your hard work in federated learning and natural. And if anyone wants to explore Nikita's work further after this talk we've had with her, feel free to check out her website at www.cs.toronto.edu/Nikita, and we'll make sure to have links to all the papers referenced in this talk as well as her website in the description somewhere below. So thank you, Nikita. Hope you have a
Thank you
great
so
day
much.
and see y'all later.